So looking at the Google Doc from rotation 1, so this is rotation 1, the Google Doc looking at calculating rotational variables. We want to identify the different parts in this problem. So this is our time. This, of course, is the radius, so that's our radius. And this angular velocity means that's omega, 2 radians per second. And we're asked to find a value of alpha, and that's using omega final equals omega initial plus alpha t works to find alpha. The final is at rest, so that would be 0, coming to a stop. The initial is 2 radians per second, and the time is 50 seconds. So if we rearrange that equation, we've got 2 radians per second. We bring this over to the other side. So it comes over here and becomes a minus, is equal to alpha times 50 seconds, or alpha is equal to minus 1 over 25 radians per second squared. And so that's our value of alpha, minus 1 over 25 radians per second squared, which you might have also found as minus 0.04 radians per second squared. And it's minus because it's opposite the direction of omega, and we just assumed that was a positive. That's our omega initial, our omega naught. Halfway through, what is each of the following? The angular speed, the linear speed, all of those things. So you can find your angular speed by saying it's equal to omega at any point is equal to omega initial plus alpha t. In this case, it's pretty easy to do. This is 2 radians per second. This is minus 1 over 25 radians per second. The time is 25 seconds, so this is pretty easy math to do. So this is just 1 radian per second, which you could have just estimated, right? It's halfway through. So the angular speed is 1 radian per second. The linear speed, that's v, the magnitude of that is r times omega. So that would be 0.3 meters because the radius is 3 meters right up here, times omega, 1 radian per second, gives us 0.3 meters per second. Notice that radians drops out because it's a unit to remind us that we're in radians, but in general, it's not a real unit like meters or seconds or something like that. So it drops out as we don't need it anymore. Okay, for linear acceleration, we have 2 things. So it's at this point. So you can measure it at any point. I'm going to do it at t equals 25 seconds because I have all the values from up there. So the centripetal acceleration is v squared over r. So that's going to be 0.3 meters per second squared over 0.3 meters, which is going to be then 0.3. That'll give me a meter squared per second squared divided by a meter, so meters per second squared. So that's as we expect. That's the value we expect. You can also calculate it by saying AC is equal to omega squared r. That's the other expression for it. And omega is 1 in this case, and r is 0.3. So you can go that way as well. The tangential acceleration is alpha times r. And so that's going to be minus 1 over 25. Again, the minus just tells you the direction. 25 radians per second squared is our units times the radius, 0.3 meters. So again, that's going to have meters per second squared. So that is minus 0.012 meters per second squared. So the magnitude of the total acceleration, this is a little odd, is that we would have the centripetal acceleration. Let's see, we draw this. I think it asks you to draw this. So I'm going to draw it again. If the point is right over here, then the tangential acceleration, if the particle is going this direction, then the tangential acceleration is going to be this way. And it's a pretty small number, right? Minus 0.012 meters per second squared The radial acceleration is a pretty long vector of 0.3 meters per second squared. The net acceleration is going to be a vector off in this direction, and I've exaggerated it. But we have a Pythagorean relationship here where this is 0.012 meters per second squared, this triangle, so we can find the hypotenuse here. So the hypotenuse is the net, is the total acceleration, the magnitude of the total acceleration. So that's going to be the square root of the sum of the squares. So I would square that plus 0.012. So it's going to be really close to our 0.3 because the other correction is really small. So if I square this and I take the square root, then I get, right, the A total is 0.3002 is where it starts to show up this correction, meters per second squared. So it's basically the same as the radial. And to find the angle, then you would say this angle, let's say theta here, you could say tangent of theta, and this is going to be a fairly big, small angle because this is really, really tiny. Tangent of theta is 0.012 meters per second squared over 0.3, so the units cancel out, which is good because we don't want to take the arc tangent of that. So theta is equal to tangent to the minus 1, 0.012 over 0.3, so that's going to be tiny. And so we get the arc tangent of that of 0.012 divided by 0.3. So that get me like 2 degrees. Okay, so that's really, so I really exaggerated this angle. This angle is really supposed to be 2 degrees, 2.3 degrees if you like. So that's how you find these values and also find the components to find all of the acceleration.